Hi, and thanks for tuning into this virtual presentation for the AIChE 2020 National Conference. I'm Julie Rorrer, and I'm a postdoc at MIT. And in this presentation, I'll be telling you about some of the work that we're doing on using ruthenium-based catalysts to convert polyolefin waste into liquid alkanes. So I put this little comic in the intro slide here because I think it does a really good job of illustrating our dependence as consumers on single-use plastics, as well as the adverse effects that those plastic materials are having on our environment after they're disposed of. So unfortunately, the majority of plastic waste ends up in the landfill or environment. But around 16% is mechanically recycled. And this offers a second life to waste plastics, but it's often referred to as downcycling because these second life plastic materials have lower quality compared to the original plastic, and we're essentially just delaying the inevitable disposal of these materials into landfill. On the other hand, chemical recycling actually breaks the bonds present in the plastic waste. And two common means of using this method to upcycle plastics are through pyrolysis and gasification. Gasification gasifies the plastic waste into syngas, which then requires further processing at chemical plants. And pyrolysis generates an oil, which also requires further refining. But there are many challenges associated with these chemical recycling techniques, and these include low product selectivity, the formation of tar and char, the presence of contaminants, and challenges associated with feeding solid plastics at high pressures and temperatures. And this results in little economic and energy incentive relative to mechanical recycling or just producing new polymers. And so to truly create a circular plastics economy, we need to be thinking about both deconstructing today's plastic waste into products and using these products and others to design the plastics of tomorrow. And these plastics of tomorrow would be infinitely recyclable by design. And while there's a lot of different approaches here, we're going to be focusing in this talk on thermal heterogeneous catalysis for the depolymerization of polyolefins into products. Specifically, we're going to be talking about hydrogenolysis as a means of breaking the CC bonds in polyolefins in the presence of hydrogen, a catalyst, and thermal energy. So this method has been used for lignin depolymerization to cleave the CO and CC bonds in these complex polymers. And so similarly, we can think about breaking down the complex polymers in polyolefins by using hydrogenolysis to snip apart the CC bonds. And so there are many advantages to hydrogenolysis, and this includes higher activity compared to thermal radical catalyzed depolymerization. It requires lower energy compared to gasification or pyrolysis. And because with heterogeneous catalysts, we can separate the catalytic material, this makes it more scalable and compatible with existing biomass upgrading systems. Finally, we could source the hydrogen renewably through methods like solar water splitting. But there are many challenges associated with hydrogenolysis, and this includes developing active, selective, and stable catalysts, tuning the product distribution, and characterizing long-chain polymer products and modeling their kinetics. So we can use model compounds to begin to understand the kinetics and mechanisms of these transformations, but ultimately, when we turn to complex feedstocks like real plastic waste, there's a lot that we don't know about what's going on inside the reactor. So if we work at the intersection of model compounds and complex feedstocks, we can begin to understand some of the kinetics and mechanisms of this reaction to ultimately design tailored active sites that have high activity and selectivity for our desired depolymerization reactions. So now that I've sort of motivated why we're going to be using hydrogenolysis as a means to break down polyolefins, I'm going to focus the rest of the talk on how we understand hydrogenolysis using model compounds and by predicting product distributions with simulations, and then how we take that understanding and apply it to the hydrogenolysis of real plastic waste. So to start, we wanted to identify some catalysts that are highly active for hydrogenolysis of N-alkanes. So we selected a variety of different noble metal catalysts from the literature and wanted to look specifically for high activity under mild conditions. We used N-octadecane as a model compound for polyethylene and studied temperatures ranging from 200 to 250 degrees C and hydrogen pressures ranging from 30 to 50 bar. And this is all done in the absence of solvent. So I won't go too deeply into all of this different catalyst screening, but what I would like to draw your attention to is the fact that ruthenium and cobalt-based catalysts showed excellent hydrogenolysis activity for this model compound for polyethylene. And specifically, a 5% ruthenium on carbon catalyst exhibited very high activity for hydrogenolysis with 92% conversion of octadecane at only 200 C. So for the rest of this talk, I'm going to be focusing on this 5% ruthenium on carbon catalyst. So if we want to look a little bit more specifically into what kind of products we actually made with this catalyst, we can collect the headspace, and we see that we're producing in the gas phase mostly C1 to C4 alkanes, so methane, ethane, propane, butane, as well as some C5 to C8 alkanes as well. And in the liquid fraction, at 92% conversion, we see a nice distribution of C7 to C17 N alkanes. But what we don't really understand still is whether the hydrogenolysis is occurring via a sequential cracking pathway of the terminal CC bond, which is shown by the red scissors, or if the CC bonds are being cleaved randomly along the polymer chain, which we can imagine with these blue scissors here. So to look into this a little bit more, we stayed with our N-octadecane model compound and looked at the effect of product distribution as a function of time. And so as we increase the time, if we start with 2 hours here, we see a distribution of C8 to C18 products. And as we continue to increase the time, we increase the conversion, and we see a shift in product distribution from these longer N-alkanes to shorter N-alkanes. And finally, this product distribution shifts further and further towards lighter alkanes until we're producing mainly gaseous products. So what this tells us is that we have a tunable product distribution with the varying extent of reaction. It also tells us that our cleavage is sequential. And because we have such a wide range of products at low conversions, this suggests that we have both terminal and central CC bond cleavage occurring. So now moving to a slightly more realistic polyethylene model compound, we have 700 milligrams of a 4,000 molecular weight polyethylene. And this is placed with our catalyst into our PAR reactor in the absence of solvent. And after 16 hours under 20 bar hydrogen at 200 degrees C, we get 100% conversion of polyethylene into liquid and gaseous products. So we have a 45% mass yield of liquid products, which comprise of a range of C8 to C30 alkanes. And in our headspace, we have mostly methane, ethane, propane, and some lighter alkane gases, C5 plus as well. So this tells us that even with solid polyethylene, the ruthenium on carbon catalyst is active for depolymerization to produce liquid and alkanes. So we're wondering if we can predict the product distributions based off of where along the carbon chain the CC bond is being cleaved. And so to do this, we turn to a kinetic Monte Carlo model. So what we're doing here is we're starting with an initial polyethylene distribution. In this case, we're starting with an average molecular weight of 4,000. And we tell the model to select a molecule in this distribution and select a probability at which a certain bond will be cleaved. So for this cut probability, we looked at a few different cases. So we'll start by looking at random scission only. So this is predicting what the product distribution will look like after 550,000 turnovers if the bonds are being cleaved randomly along the molecules and the molecules are being selected randomly across the distribution. So if we see here, even if we optimize this reaction and this model, we don't get a very good fit of the model to the experiment. If we only consider terminal scission for our imposed cut probability, what we see is that the model also does not fit. We get a huge amount of methane formation, which you can barely see here on the left of the model, and we get a very wide distribution of carbon number products centered around 250. But if we have a weighted mix of both terminal and random CC bond scission, we can get a form of the model which much better represents our experimental results. So while this model is still in progress, we can see that the model with both terminal and random scission fits the best. And so for future work, we're really going to be understanding better how we can use our kinetic experiments to look at the effect of chain length on CC bond cleavage selectivity, and also think about how we can characterize mass transfer in the polymer melt for those more complicated longer chain alkanes. So now that we have a little bit of an understanding of hydrogenolysis with our model compounds, and we know that both terminal and central CC bond cleavage is occurring, we can use these optimized conditions for the hydrogenolysis of real plastic waste. So what we did here is we took a used VWR solvent bottle and cut it up into tiny little pieces. and added it directly to our reactor with our catalyst. And after 225 degrees C for 16 hours under 22 bar of hydrogen, in the complete absence of solvent, what we see is that we get a 53% liquid yield to N-alkane products ranging from C8 to C30. And if we remove the catalyst just by centrifuging it and no other pre-treatment or post-treatment, we can see that we have this really nice clear solution of alkanes. And so this tells us that the ruthenium on carbon catalyst can effectively depolymerize genuine post-consumer plastic waste under mild conditions. And I'd like to point out that this plastic bottle that we used was a high density or a low density polyethylene, which is comprised of many different branches. And so we thought, well, why don't we test a material with all branches and see if this catalyst works with polypropylene as well. So under similar conditions, we put our polypropylene beads directly in our reactor with no pre-treatment, add in our catalyst. And after 16 hours at 225 degrees C, what we see is a range of different isoalkane products between C8 and C34 at 100% conversion. And so this tells us that the ruthenium on carbon can also effectively depolymerize polypropylene into liquid and gaseous isoalkanes. So for ongoing work, we'd like to really expand the scope of substrates that we can study with this ruthenium on carbon catalyst, including different forms of high and low density polyethylene, as well as some compounds with CO bonds as well. We also want to look and see if we can manipulate the active site to control our selectivity and activity. We could do this through changing the support to introduce bifunctional effects and by changing the nanoparticles that we're using. We could also consider using confinement effects like in zeolites to control our mass transfer and thus control our selectivity. Ultimately, looking forward towards mixed plastic streams, we'd like to be able to use this technology to enable selective catalysis of different types of plastics in a complex stream. So you can imagine under mild conditions, we could first cleave CO bonds in materials like PET, and then at slightly higher temperatures, we could start to cleave CC bonds in linear polyethylene, and finally break down the more branched bonds in polypropylene as well. And this would involve tuning the CO and CC bond cleavage activity so that we could really effectively utilize these waste streams. So this will all require assessing the performance with both model and real compounds. So to conclude, I hope I've showed you that hydrogenolysis is a promising method of upcycling plastic waste, and that ruthenium-based catalysts are very active for this reaction and enable sequential CC bond scission. And finally, that these catalysts can be used for the depolymerization of real polyolefin waste. So this work has been accepted for publication, but before it appears in Jack's Gold, you can check out the preprints on ChemArchive. With that, I'd like to thank Professor Yuri Roman-Leshkov and the Roman-Leshkov group at MIT. I'd like to thank our collaborators at NREL, as well as the other members of the plastics team in our group. And I'd like to thank NREL and Bottle for funding this research. Finally, thanks again for tuning into this presentation, and I look forward to the question and answer session. Thanks.